Good morning and welcome to our fourth Engineered to Perform webinar. My name is Deborah Golden and I am the Inside Sales Representative at Swagelok, Michigan, Toledo, and I will be your host today. Today's discussion is on elastomers and their chemical composition and how they can affect your critical operations. Our guest today is Marcy McQuarrie. Marcy has gained broad depth of knowledge regarding Swagelok products and processes during her 20 years as an engineer for Swagelok. Marcy holds a Master's of Polymer Science degree from the University of Akron and is a subject matter expert and key resource for selecting and specifying elastomer seals in Swagelok products. Now, before we get started, I have a few housekeeping notes for you as it pertains to our dashboard. You will notice that there are several widgets at the bottom of your screen. The first is the speaker bio page where you can learn more about our guest today. And also there is a slide widget. You will notice the On24 screen is not like other webinars. You have the ability to move the boxes on the screen by clicking and dragging them to any area that's comfortable for you. We also have a widget for Q&A. So as you listen to the presentation, think about what your elastomer questions are, and you can type them in at any time. And finally, there are links to our LinkedIn page and contact page. So today's webinar is also very interactive. We want you to ask questions and respond to our polls. Now I'll turn it over to Marcy. Marcy, welcome, and thanks so much for being with us today. We're looking forward to you helping us understand more about elastomers and the importance in chemical processing.
Okay, thank you so much. Welcome everybody, and thank you for joining us this morning. I'm hoping that you find the webinar very helpful. As Debbie said, I've been with Swagelok for 20 years, and I've seen a lot of questions and a lot of confusion regarding this topic. So my goal here really today is to try to demystify the whole topic of elastomer seals for you a bit, and at least get you in the direction of knowing where to go to ask questions and how to ask the right questions. So this morning, what we're going to do is look at 4 basic seal materials. I realize that there are many more than these 4 materials, but what I've learned is if I can get a better understanding of these 4 materials, you're pretty much really on your way to understanding elastomer seals. And then it's a much easier task to pick up any remaining materials after you get these first 4 under your belt. So in addition to talking about these 4 materials, I want to show you how to use chemical resistance guides that you may find online and what to look for and which ones are good and provide information that's helpful to you and which ones probably don't help you as much as you will need in your systems. I also want to share with you some common compatibility issues that I've seen over the last 20 years. At least if we can click these ones off your list, you'll know what to steer clear from, just from experiences of other troublesome media. And then just real briefly, we're going to talk about some failure analysis and what to look for if you're trying to figure out what's gone wrong in your system. Then we're going to move on to talking about some commonly misunderstood topics, namely rapid gas decompression, which I receive a lot of questions on, shelf life, and NACE. All right? So let's move along here. So Debbie, it looks like there's a poll question. So the first poll question is, what resources do you use to select an elastomer seal for your system? Okay, so I see your answers there. And that's helpful to guide me through this presentation with you. It looks like there's a pretty divided list of sources there. And then finally, what challenges do the elastomer seals in your facility face for you? And that will also help me lead the discussion here a bit. Okay, so no surprises there, high temperature and chemical interactions. I'm surprised there were no low temperature issues or low temperature challenges. So let's move along here. I've tried to teach this course without this first slide, but I have found that really the root of most of the confusion with elastomer seals really starts way back in understanding the supply chain. The reason why I want to explain to you the complexity of the supply chain for elastomer seals is a lot of times I see engineers and plant personnel asking the wrong person in the supply chain your technical questions. So just to gain an understanding together of the supply chain for elastomer seals, let's start with the raw gum rubber. So the raw gum rubber is manufactured by the large companies that most likely you are familiar with. That would be DuPont and Solvay. Those companies, which names I'm sure you're familiar with, are the companies that are manufacturing the gum rubber that's used in your elastomer seal. Now, if you look at the picture that I have there for gum rubber, you can see that it looks nothing like a seal material. And in this form, gum rubber has really no useful properties to us as seals in our processes. Okay? From there in the supply chain, that gum rubber then goes to a rubber compounder. And what a rubber compounder does is take the raw gum rubber and add their list of ingredients to create a compound. So a couple things here. The first thing is there's a new word for you, which is compound. I've noticed a lot in elastomer seals that end users aren't familiar or aren't sure what to even refer to the elastomer material as. So when you're talking elastomer seals, compound is going to refer to a particular recipe for that material. So a lot of times I hear engineers incorrectly referring to the elastomer material as resin or what grade or what lot. And all of that sort of creates the start of the communication problems, because what you need to be referring to is a compound and a compound number, which is a specific recipe for a seal material that you may be using. The next chain in the supply chain is the O-ring manufacturer. Sometimes the rubber compounder and the O-ring manufacturer can be the same company, but that's not always the case. So in the case where an O-ring manufacturer will just purchase a rubber compound, from a compounder, and then mold the material into the O-rings themselves. From there, those O-rings are typically sold to a distributor. So imagine if you're an O-ring manufacturer and you're manufacturing a mass quantity of O-rings. It'll be very difficult for you to sell small numbers of O-rings and have a profitable business. So for the most part in this industry, O-rings are sold to a distributor. The O-rings then are purchased from companies like Swagelok through a distributor and placed into our products. So why do I review this with you? Well, a lot of engineers will call the gum rubber manufacturer or look at the gum rubber manufacturer's data sheets for information about their seals, which is information that the gum rubber manufacturer doesn't have because they did not create the recipe used to manufacture the elastomer material that's in the O-ring. So hopefully you can understand that. Another common mistake that I see is engineers will contact the distributor of the O-ring manufacturer, and they also don't have the information that you're asking them for because they are simply just buying and selling elastomer or O-ring seals. So the people that you really want to go to with those questions when you're asking about performance of a particular seal is going to be the rubber compounder. They're the ones that have formulated the recipe to meet certain mechanical properties. Okay? So is everyone okay with me there? Okay. Let's move on. If you'll notice, there is a lot of confusion around elastomer seals, and it's very difficult to get information. And the reason why I included this here is just so you can understand some of the mindset of this industry. The rubber compounders really felt early on that the success of their company's base was based on their particular recipes that they developed. And there is a lot of secrecy around maintaining the ingredients or what goes into those particular compounds. And I have found that even though that much may not so much be the case, still the mindset exists today, and it becomes very difficult to get information about particular compounds. So if you couple that with the other facts that we have many people that aren't asking the right person in the supply chain, and then we have the secrecy, it adds to a lot of confusion about our seal materials. So how does Swagelok maintain, how do I as Swagelok's polymer engineer manage this secrecy and this information that is critical to understanding how the seals are going to perform? So for every seal material that is found in a Swagelok product, I create a Swagelok material specification. What you can see on the screen is an example specification for an FKM elastomer. And the most important part of this specification really is that third section that defines the approved compounds for a particular seal that can be used in one of our products. So what I do to specify is I call out the O-ring compounder and their recipe. That way I know specifically what the expected properties are for that seal material. So if you're in a situation where you're specifying elastomer seals for use in your processes, you need to make sure that you're asking your sourcing folks to purchase those seals to a material specification. And assuming you're the one writing that material specification, it's really important for you to define which O-ring manufacturer and compound is acceptable for use in your process. Here I'm just showing you what a typical compound recipe might look like. So the first item that I have there on the list is polymer, and that really is just referring to the raw gum rubber that is sold by the big companies that you're familiar with. So DuPont, Solvay, Dyneon, their ingredient, their raw gum rubber is just the one of many ingredients that are going to go into your O-ring compound. You can see that there's other items in there. There's fillers and oils and activators, vulcanizing agents, so many other things in addition to the raw gum rubber. So you may then ask me, well, how come DuPont and Solvay and Dyneon, companies like that, have material data sheets that call out properties? You have to understand that those properties are for a test compound that they've developed for their particular raw gum rubber. But those test compounds are not sold for use by companies like Swagelok and your company. They're just test compounds for their raw gum rubber. So you have to be really careful when you look at data sheets from the companies that are just making the raw gum rubber. Okay, so I don't want to get too deep into understanding a lot of terminology regarding polymers, but there's just a few terms that I want you to understand moving forward. The first one is just understanding what a polymer is. There's a lot of confusion about what a polymer actually is, and quite often when I ask people what is a polymer, I get the answer, it's a plastic or elastomer. And that really isn't the correct definition of a polymer. A polymer is really just a large molecule. So it's really the study of macromolecules, and it's made up of many repeat units of a particular molecule. So to give you sort of a catchphrase to remember, all plastic and elastomer materials are polymers, but not all polymers are plastics and elastomers. So there's many materials out in the world, naturally occurring and synthetic, that are polymers that are not elastomer and plastic. The next thing that I want you to be aware of is a term called vulcanization. If you haven't heard of the term vulcanization, you may have heard of the term curing. This is important for elastomers because this is what provides the mechanical properties that are necessary for an elastomer material. So when you hear of the word vulcanization or curing, what that's referring to is taking your very large, very long chain molecules, which you can see in the bottom picture on the left-hand side, and you're turning it really into a network of material. So after a polymer is vulcanized, you can see now on the right-hand side those connections between the long chains, which are depicted by the red dashes that you can see. Those are areas where those chains are linked together. So now imagine that this material is more like a net. And if you think about your kids' soccer and the net that catches the ball, we know that when the ball is kicked into that net, what happens, that ball bounces back. So because of that net and the network created by the individual strands, there's a property created there, which is elasticity. So that's what is referred to when you hear of vulcanization and curing. Both words mean the same thing. Okay, so we're going to move into the first of the four materials, and I think once you get some confidence and better understanding of these four materials, you'll be well on your way to understanding what seals are in your products and in your equipment and how you would expect them to perform. The first one we're going to talk about is ethylene propylene. Ethylene propylene is really a very general purpose elastomer. I think it's the easiest one to understand, and we'll go through that here this morning. The thing that I want to point out that's really important, if you're taking notes, one of the really important takeaways here is this group of elastomers is only for parts of your process where chemical resistance to petroleum-based fluids is not required. So for ethylene propylene rubber, we're going to talk about some names, cure types, the temperature range, and chemical resistance. The first thing that I want you to understand about ethylene propylene rubber is that really its claim to fame is weatherability. It's used most commonly in automotive sealing systems, window seals, hoses, and you can see their roof sheeting. That black material that you can see on the picture on the right is commonly ethylene propylene rubber. It's also used commonly in ponds as pond liner. You see the black sheet liner that's laid down first in those pond or water installations is also ethylene propylene. So when you think of ethylene propylene, think of great weatherability characteristics and not resistant to petroleum-based chemistries. I have the temperature range at the top, but I want you to understand that this doesn't mean this is for any particular ethylene propylene compound. This is the range for all compounds. So a particular compound will lie somewhere within this range, but certainly won't cover this entire range. That's something to be aware of when you're using ethylene propylene seals, is to know which one that you have and what range, what portion of this range that it covers. So now that you understand what cure types are, we're going to talk about cure types for ethylene propylene materials. There are generally two types. There's peroxide cured and there's sulfur cured. The first one, ethylene propylene, can only be peroxide cured. So if you see, sometimes you'll see when an ethylene propylene material is specified, it will either say EPM or EPDM. And there's a clear distinction between the two. The one at the top, if I have any chemical engineers in the audience, you can see that it's made up of ethylene and propylene, and then you can see the repeating units of ethylene and propylene there. But the thing that you don't see in the top is you see no double bonds. So for those of you that do not have a chemistry background, a double bond I'm referring to simply as a chemical bond that is connecting the elements together. Single bonds, you can see, are depicted in the chemical structure above just by the dash mark. A double bond you can see below, as in the terpolymer. It looks like an equal sign. That's not an equal sign. That is a double bond. The reason why I mention this, in order for sulfur curing to be possible, there must be a double bond present. So we have ethylene propylene monomer in the top, which can only be peroxide cured because there is no double bond available to make those linkages necessary to get your elastomer properties by sulfur curing. On the bottom you can see you have ethylene and propylene plus a diene, and that diene provides the double bond that's needed to enable sulfur curing. So let's take a look at what the difference really means to us between peroxide curing and sulfur curing. For the most part, the benefits really are not for the end user in the case of type of cure for EP rubbers. The benefit really here is for the rubber compounder and manufacturer. There are some differences in properties between sulfur cured and peroxide cured, but for the most part, the driving force to actually develop EPDM was to allow sulfur curing. So one of the things that I want you to note on the bottom right-hand side is if you look at curative price, it's lower for sulfur. So really the driving factor here is in cost of producing EPM versus EPDM rubber. Now there are some differences, and if I can go a slide back here, peroxide cured compounds are generally preferred over sulfur cured types for improved heat resistance, radiation resistance, and compression set, while sulfur cured typically have higher tear strength and abrasion resistance. So I don't want you to think that the only driving force is really the cost of manufacturing and the ease of sulfur curing. There are some differences between the two elastomer materials. Again, the biggest thing that I would like you to remember from this presentation in regards to ethylene propylene rubber is that petroleum-based fluids and lubricants are not compatible with Hnbr seals. Why this concerns me so much is if you think of what types of lubes are commonly out in your shops or in your maintenance areas, are probably petroleum-based lubes. So I think the use and popularity of petroleum-based lubes makes me a little bit nervous when there's Hnbr seals in your valves and your processes. Personally, I think you need to have a really good reason to use EP seals. Otherwise, this threat of having your seals come in contact with a petroleum-based fluid sort of makes it not worth it for me as an engineer trying to put seals in my processes that have the least opportunity for problems. So if we look at the places where chemical resistance is favorable, Skydrol or phosphate ester-based hydraulic fluids is one area where I think it's definitely acceptable to overlook the problems with EPR and petroleum-based fluids because of its tremendous chemical resistance to Skydrol. Steam is another one. And then also if you have weathering concerns, ozone, and radiation concerns. So it's not compatible with strong acids, mineral oil products, and petroleum-based fluids and lubricants. Okay, so how are we doing so far? Everyone on board? I sent out another pulse check there. Okay. So just to recap for our first material that we're talking about, which is ethylene propylene rubber, we now understand that in this category there's ethylene propylene monomer and ethylene propylene diene monomer. And really the biggest difference between the two is that EPDM can be sulfur cured or peroxide cured, and EPM can only be peroxide cured. There is a fairly broad temperature range from -54 C to 150 C. However, please understand that that doesn't mean for any one particular compound is going to be suitable for that entire range. This is the total range that is possible for EPR seals. And then finally, we're going to remember that EPR is not compatible with petroleum-based lubes. Okay, let's move on to FKM. The next type of material is a Floral Elastomer, and this is for use and service when resistance to prolonged exposure to higher temperatures and or petroleum oils is required. What we're going to talk about is the names and common trade names for FKM, the types of FKM that are available, the temperature range, and discuss chemical resistance. Okay, so everyone that's had my class before on Elastomer seals know that I always go into a spiel about trade names. And while I have no personal problem with trade names from a technical perspective, as an engineer, I can tell you that trade names really get in the way of having beneficial conversations about what seals to use and where to use them. So one of the things that I always challenge my students on is, if possible, please do not speak in terms of trade names when you're referring to FKM elastomer. That's going to make more sense to you in a few minutes here. But a great habit to break is the use of trade names when referring to FKM materials. So FKM has very good resistance to temperature and many different chemical streams that you may have in your process. I want to talk to you this morning about why that's possible. I hate to show you a picture of the periodic table, but there's something that I want you to understand, because you probably are aware that FKM performs better than other seal materials. You understand that it's a step up. But part of the problem I think that makes this topic so difficult is if you try to just remember but you don't have an understanding of why, I think it makes it very difficult to maintain an understanding. So we're going to spend some time understanding what's so special about FKM elastomers. Why do you get better temperature, a broader temperature range, and why do you get better chemical resistance? And to start that conversation, we really have to take a look at the periodic table. So if you locate fluorine on the periodic table in the upper right, one of the things that I want you to understand is that it has the most electronegativity of any other element on the periodic table. And what does that mean for us? That means the bond association energy for a carbon-fluorine bond is higher than any other combination possible with carbon. So if you look at that box of bond dissociation energies, you can see that it takes more energy to break a carbon-fluorine bond than anything else that's shown there in the box. And because of this, you as a result, you get the broader temperature range, it can handle higher temperatures, and you get better chemical resistance. That's really not the whole story, though. Not only do fluorocarbons have this carbon to fluorine bond, it has a very high ratio of those bonds. So you can look at the segment of the polymer that I'm showing you there, and you can see there's a very high percentage of carbon to fluorine than carbon to hydrogen. So not only do we have the strongest bond possible, but we also have a high percentage of that bond. The next thing that makes FKM material higher performing is that you can see those bonds, and I've talked to you briefly about this. Those dash marks that you see are referred to as single bonds. When you have a single bond or a polymer that has nothing but single bonds, it's referred to as saturated. And why we care about that is because it makes the polymer very stable. There's not a lot of opportunities there for bonds to be broken. In other words, if we had double bonds in there, there would be a higher opportunity for those double bonds to be broken and form with something else. But in fluorocarbon elastomers, the backbone is completely saturated. Okay, this next slide really tells the whole story with FKM and why I want you to break the habit of talking in trade names. The thing that you have to understand with FKM elastomers is that there are many types. So the first thing that I want you to look at is the triangle on the left. The triangle on the left has 3 possible monomers there. At the top, you see HFP, which stands for hexafluoral propylene. On the bottom, you have TFE, which stands for tetrafluoroethylene. And then you have VDF, which stands for vinylidene fluoride. So when the raw gum manufacturers are making FKM raw gum, they can use any combination of those 3 to develop certain types of FKM elastomer. So if we are going to speak in trade names for a moment, if you've heard of Viton A, that particular raw gum is only made up of hexafluoropropylene and vinylidene fluoride. A type 2 would have all 3 monomers present, so hexafluoropropylene, vinylidene fluoride, and tetrafluoroethylene. So why do I mention this? Because the raw gum and the resulting seals are going to have different properties based on the ingredients that are used to make that raw gum rubber. So if you come to me or some other technical expert and you ask them, hey, I have Viton as a seal in my application, the first thing, I already don't know what type of FKM you're referring to. Are you referring to a type 1, which will have very distinct properties than a type 2? To complicate this a bit more, there were more recent developments to develop a third type of FKM, which provided better low temperature performance. So the polymer engineers developing the raw gum rubber for FKM discovered that if they replace hexafluoropropylene with PMVE, which stands for perfluoromethylvinyl ether, they could develop raw gum rubber that, when turned into an elastomer compound and a resulting seal, much better low temperature properties can be achieved. So just by looking at those first three types, now that you can understand, using the trade name Viton, really you've lost a lot of opportunity for communicating information between yourself, other people specifying equipment and seals in your processor, your valve supplier. There's a lot of information that's lost just by using such a generic term. So a good habit to fall into is instead referring to FKM and what type of FKM, namely type 1, type 2, or type 3. There are two additional types, but they're not commonly used, so we're going to just limit our conversation to the first three, and I think that's enough for our first discussion on this topic. So let me send out a pulse check and see how we're doing. Seems like everyone is still with me, which is good. Okay, let's move on. Actually, I want to go back for one quick second. So one of the things that you can see with the different types of FKM is that the percent fluorine changes with the type of FKM that's manufactured. That percent fluorine is important because it results in chemical resistance for your elastomer seals. So the higher the fluorine content, the better chemical resistance it has. However, I can absolutely promise you, in the world of elastomer seals, it's always give and take. So if you've gained something, I guarantee you've given something up to gain that. So in this case, we can gain chemical resistance, but oftentimes we lose low temperature performance. This is why there are so many various O-ring compounds out there, because there isn't just one FKM or one EPDM that's going to satisfy all customers' uses. What the O-ring, the raw gum rubber manufacturers do is produce a variety of raw gum rubbers that can be used to manufacture O-ring compounds and seals that can be used in many different applications. So you can see here with the chart on the right that as the percent fluorine is increased, the low temperature performance is changed as well by that difference in fluorine content. So the main takeaway here is understand that there are three main types of FKM, type 1, type 2, or type 3. They all vary in chemical resistance and low temperature performance. So when specifying, you need to understand which type of FKM that your seal material is made from. Finally, on this topic, I want to point out that you have to be really careful of continuous use temperatures. And please be very careful about information that you find on material data sheets that will often list a high temperature But the thing that they do not explain on those data sheets is that those high temperatures are not for continuous use. Try to put this in a more simpler term. If you got in your car today and from now on, for the rest of the time you own that car, you drive as fast as you possibly can, your car is not going to last as long as if you drive it moderately, correct? So it's the same thing with elastomers in our valves and other equipment that has seal components that are used in our processes. The more you push them to that high temperature, the shorter their life is going to be. That's just a fact of life that you have to accept. So if you see a data sheet and then you compare it to a Swagelok product, and you see that the high temperature rating is lower for a Swagelok product than reported on a temperature or on a data sheet, it's because we want to give you as long a service life for the product as we can. So that means that oftentimes we have to back off that high temperature value that you see on the data sheet. Another thing that's important in understanding which type of FKM that you have is the variation in chemical resistance. So if we look at the table in the top of this slide, and let's take a look at the row that says hot water, steam. So if you see the first column there that says fluorocarbon, type A, which would be Viton A, which would be a type 1 FKM, it has moderate to severe effect from steam. However, you can see that the other types of FKM are recommended for use with steam. This is why you need to understand which type of FKM is used as the seal material in the products that are used in your processes. I've also included a list of chemicals that are known not to be resistant to FKM. And you can see next to methanol in both steam, that applies only to the type 1 FKM. So hopefully that gives you a much better understanding of FKM seal materials. I know that you're going to work hard with me not to refer to FKM by their trade names only, because that is going to hamper our discussions and our progress in making sure that the right seal is in the right application. You now know that there are 3 main types that vary the monomer that's used in the manufacture of the raw gum rubber, and that properties for that FKM and those various types fluctuates based on the elastomer type. With that being said, then now you can clearly understand that the temperature of which FKM seals can perform at depends on the type, as well as chemical resistance also depends on the type of FKM that's used to make the seal component. Okay, so I think we have those 2 materials under our belt now. We have a better understanding, hopefully, of ethylene propylene rubber, and we now hopefully have a much better understanding of FKM materials. Now let's take a look at Hnbr. Hnbr stands for nitrile rubber. You also may hear it referred to as Buna-N. So Hnbr, nitrile, and Buna-N are all referring to the same type of elastomer material. So I think something that can help you keep these materials straight is try to think as Hnbr, sort of almost an opposite to ethylene propylene rubber. Whereas we knew that ethylene propylene rubber is not resistant to petroleum-based fluids, this is where Hnbr tends to shine as a material. So they're almost completely opposing each other in terms of chemical resistance. So you should never find yourself in a situation where you're trying to determine between the two and which to use in your process, because they would be used in completely different situations. Okay, so while going through Hnbr this morning, we're going to talk about names, properties, temperature, and chemical resistance. If you remember back to our discussion on ethylene propylene, that was elastomer that was made up of two monomers, ethylene and propylene. And if you think back to our discussion just a few minutes ago on FKM, there were various monomers that are used to make FKM, two being hexafluoropropylene and vinylidene fluoride if you're going to create a type 1 FKM. For nitrile, Buna-N or Hnbr elastomers, they're made up of two different monomers, acrylonitrile and butadiene. So why don't I explain to you that there's two different monomers that are used to make this material? The reason is when I have more butadiene in the compound, in the raw gum rubber, it increases the elasticity, the low temperature flexibility, and it creates a cross-link site. So butadiene contributes that portion to the overall elastomer. If we look at the acrylonitrile side, it imparts hardness, tensile strength, abrasion resistance, and fuel and oil resistance. So remember when I said not too long ago, there are many, many different compounds that are developed for these materials because one compound is not going to be suitable for all applications. So nitrile compounds are made of raw gum rubbers that have varying degrees of acrylonitrile and butadiene. There is a vast difference from one nitrile compound to another, as the acrylonitrile content can vary greatly between 15 and 50%. So as the compounds that have a higher acrylonitrile content, they're going to have better resistance to oil and fuel. However, you're going to give up low temperature performance. So remember when I said a while back, I guarantee in the world of elastomers, if you've gained something, ask yourself what you've given up. If someone comes to you and says this has better resistance to fuel, think to yourself, okay, what did I just give up? And in this case, you would be giving up low temperature performance. In general, the nitrile elastomers can be used up to 100 degrees C with shorter life at 121 C. That goes for the same thing that I just explained to you about FKM. If you're going to push them to that upper limit all the time, you are going to be shortening the life of that elastomer seal. So be careful when you're pushing these seals to their upper rated temperature for long periods of time. The cold temperature flexibility can vary quite a bit, ranging from -34 to -57 C, based on the specific nitrile compound that you have. I also want to explain, if you've seen in a Swagelok catalog the term Buna-C, this is Swagelok's attempt to sort of help the end user understand the variation in these nitrile seal compounds. So Buna-C refers to those elastomer materials that are compounded specifically for improved low temperature performance. If we look at the chart that you can see here, you can see as acrylonitrile content goes up, volume change goes down. That's an indication of better chemical resistance. So as an elastomer is interacting with a system media, it often will swell. So commonly, volume change is something that's measured when you're looking at the chemical resistance of an elastomer material. So you can see as acrylonitrile is increased, volume swell goes down, indicating that it has better chemical resistance. If you look at the blue line, however, you can see that as acrylonitrile goes up, the blue line goes up, which means low temperature performance is decreased. So again, with nitrile rubber, it's very important to understand specifically what O-ring compound is being used for your seal material, so you understand chemical resistance and the temperature range which that compound can successfully make a seal. If we look at chemical resistance, these materials are particularly useful when you're trying to seal in systems containing petroleum oils and fluids, dilute acids, and water below 100 degrees C. If you remember not too long ago, I said that EPDM, or EP rubber, and nitrile sort of oppose each other. Look at what is considered not compatible for nitrile rubber. You have ozone, sunlight, and weathering, which, remember, were all very good for EP rubber. From time to time, I get questions regarding Hnbr and the question of what is Hnbr and how does it perform differently? So if you look at the chemical structure that I have there on the left, hopefully now that you can see the very first part of that structure is the acrylonitrile side with the butadiene. However, if you look at Hnbr and you can see what's different between the two, you'll notice with Hnbr there is no double bond present in the butadiene portion. So we would say that this backbone here is saturated, and as a result, we understand now that these materials with saturated backbones have improved resistance to certain chemicals. So as I hydrogenate that butadiene and get rid of the double bond, which you can see for Hnbr, I've improved ozone resistance, I've improved heat resistance, resistance to explosive decompression, and the list of chemicals you can see there. And that is because we've removed an opportunity for reaction that was in the main chain of Hnbr, which is no longer present in Hnbr. So just to review, we understand that nitrile rubber and Buna-N are both terms used to describe Hnbr compounds. You also will understand that Buna-C is a Swagelok term referring to those compounds which are particularly formulated for low temperature performance. Hopefully now you understand that the actual properties of a particular Hnbr compound is based on that ratio between acrylonitrile and butadiene, and that there are many, many compounds which have various ratios of acrylonitrile and butadiene. So again, it's important to understand as an engineer specifying seals in your equipment that you understand specifically which compound you are using. For these materials, you can achieve sealing up to 121 degrees C, but these are time-dependent materials, so you need to be careful if you're going to be pushing them at the high end for extended periods of time. The main categories for chemical resistance for this material would be oils and fuels. Okay, we're going to move on to our last category, which is FFKM. We're going to talk about trade names again. And for FFKMs, it's really all about specialty compounds, and I'll share some of those specialty compounds with you. We'll talk about temperature and chemical resistance. So if we look at the chemical structure here of FFKM, and based on what we've learned so far about FKM and why it's such a great material for a higher temperature range and a broader chemical resistance, we can see that in the chemical structure of a molecule of FFKM that we have near complete carbon to fluorine bonds. This is referred to as fully fluorinated when the only bonds present are between carbon and fluorine. If you look at my little box with FKM, we can remember that not all the combinations in the main chain were carbon and fluorine. We had some instances of carbon to hydrogen, which sort of presents the chink in the armor, so to speak, for FKM. Some common trade names that you may be aware of is Calres, that is manufactured by DuPont. Green Tweed manufactures Chemres. There are also additional trade names out there, such as Simres, Perlast, and Puraflor. These materials are developed with very specific intentions for chemical resistance, and more so than the previous materials that I discussed, you really need to understand what compound and what compound number is being used as your sealing materials because they are developed for different intentions. Calres 4079 was one of the very first FFKM compounds really to market, and it was for a long time the standard FFKM compound. However, that is being phased out by DuPont and is being replaced by Calres Spectrum 7075. I don't want to go through the whole list there, but you can read the wide list of compounds and what their intended uses are. So another popular one is Calres Spectrum 0040, which is used in Swagelok products when improved low temperature performance is required. So the key takeaway here is to always verify your system compatibility with the FFKM manufacturer to make sure the specific grade of FKM that you're using is compatible with your system media. Another thing that I'd like to explain to you about data sheets is you'll see that the upper service temperature limit on data sheets are much higher than often will be the product rating. The reason for that is because the thermal expansion for FFKM is 3 times the rate of thermal expansion for any of the other elastomer materials. This can create great problems when you're using the same O-ring groove in a product and limits the upper use. So again, make sure that you have use great caution when you're referring to a raw gum manufacturer's data sheets, because they're not considering such things as the real estate that's available in an O-ring seal groove. So again, not all valve products are rated as above. Temperature ratings are based on product and the specific FFKM compound. And just to reiterate, the reason for that is because FFKM material has up to 3 times the thermal expansion of other elastomer seal materials. So you have to factor that in when you're using an FFKM seal as an O-ring material. Another thing that's not very well understood is low temperature performance of elastomer materials. It's not well understood that the system pressure affects the low temperature capability of your seal material. As a general rule of thumb, for every 750 psi in pressure, the TG will increase by 1 degree C. So let's talk about glass transition temperature for a second. This might not be a term that you're familiar with. Elastomer materials are very flexible when they're above this temperature that's referred to as the glass transition temperature. When an elastomer material is below the glass transition temperature, it will be very rigid and segmental motion of the polymer chains is stopped. Therefore, when an elastomer seal material is below the glass transition, it is not effective as a seal material because it's not able to have elastic properties. So again, watching data sheets, if you're looking at a data sheet and it provides a glass transition temperature, understand that that is for atmospheric pressure, and that glass transition temperature will increase by 1 degree C for every 750 psi. So for FFKM, you can see that the list of chemicals that it is not compatible with is fairly short, and hopefully now you have an understanding of why that is based on the chemical structure of FFKM. For the most part, the only things not compatible with FFKM are other fluorinated media. So to recap for FFKM, we understand that there are several different trade names and several different specialty compounds that are intended for specific conditions. Also now you'll understand that the temperature and the chemical resistance depends on the specific FFKM compound that you have in your application. Okay, I'll send out a pulse check, and hopefully we have a much better understanding of these 4 basic seal materials. And I think, as I said, those 4 basic materials should cover most of the seals used in your applications. I want to share with you for a moment about chemical resistance guides. I often think that if the internet was available while I was in college, how much easier my college time would have been. However, as users of that information, we all have gained an understanding that not all data out there is created equal. And I want to share with you what to look for when you're using chemical resistance guides that you find online or elsewhere. I ran through a little exercise here in that I took a chemical resistance guide that I found on the internet, and I selected methanol or methyl alcohol as my fluid stream, and that the material I would be using with that was FKM. You can see that the rating that it gave me there was a moderate rating, telling me that its performance would be fair. Now let's look at another chemical resistance guide. Here's a chemical resistance guide that actually you can find from DuPont, which I use all the time. But let's look at the differences in the information that it provides. If I do the same thing and I select methanol or methyl alcohol as my system media, and we look at the table on the right, if you notice for Floral Elastomer, it breaks it down between 2 types. The first type is a dipolymer, which we now know is type 1. That's the FKM that is formulated with hexafluoropropylene and vanillidine fluoride. It gives me a chemical resistance rating of 4. If I now look below that and look for Floral Elastomer, that's the terpolymer, that would have 3 of the monomers present that I showed you on that triangle, the chemical resistance is very good. The thing that I don't like about the first chemical resistance guide is that it didn't discern the difference between the types of FKM. Therefore, as an engineer specifying seals, the information isn't very useful to me because I don't know what type of FKM the data represents. So my recommendation to you is if you're using chemical resistance guides such as this, please make sure that it does break down the difference between the FKM types. If it doesn't, you don't know which type they used in the testing to develop the data for their guide, and unfortunately, I don't see how that data is useful to you. So be very careful to make sure that the guide gives you enough information that you could know specifically which elastomer material is being used. Now I'll quickly run through some common problems that I've seen through my career. You wouldn't think steam could cause so much trouble to elastomer seals, but this was a seal that was actually returned based on a customer that was using a seal in a steam application. Again, the thing that I want to point out to you is if you look at the FKM entries, the FKM type 1 is not compatible. However, a type 3 FKM is compatible. So again, you need to know, especially when using steam and FKM, which type of FKM is in your system. When you get above 300 degrees, even FKM and steam is going to be a challenge for you. In that case, you're pretty much left with FFKM is your only seal choice. Ammonia is very troublesome media for FKM. So for systems having ammonia in them, you want to steer clear of FKM as your seal material. Methanol and methane as well are instances where you need to understand which type of FKM that you have in your system. Notice from the information on the slide that not all types of FKM are compatible with methane. So again, you need to understand which type you have in your system. We talked about this, but it's important enough to reiterate that petroleum-based products with EPDM can cause deterioration of your seal material. So be very careful with using EPDM in environments that create exposure to petroleum-based fluids. Sour gas is another environment that creates challenges for seal materials. And the best recommendation that I can give you here is you need to understand what's in your system very carefully. You need to understand what your H2S concentration is, whether it's in the parts per million or above, will help you determine which elastomer material will work in your application. I almost feel sorry for anyone with ethylene oxide in their systems because ethylene oxide is just pretty brutal to elastomer seal materials with huge effects on the seal materials. The best advice that I can give you there are to look at elastomer, the specific elastomer compounds that are known to work with some success if you have systems with ethylene oxide. There are a few compounds by DuPont, 6375 and 2035, which have found some success in systems with ethylene oxide, but a very tough application for elastomers. And then finally, I wanted to mention refrigerants. Not only are refrigerants very aggressive to your seal materials, it's often overlooked that the oils that are used in the compressors in those systems may cause compatibility issues with your elastomer seals. So you need to not only ensure that the refrigerant in your system is compatible with the seals, but the oils that are used in the compressors in those systems are also compatible with your seal material. Just to discuss some common failure modes, namely those are rapid gas decompression, which really you can only oftentimes see by taking a cross-section of your failed seal material. If you look at a cross-section of that material, you can see the cracks and voids in your seal, which would provide you with a strong indication that your seal has experienced rapid gas decompression. Typically, when a seal material has seen high temperature effects, it will look cracked and brittle, which is often very different, not always the case, but often very different than a seal that has been exposed to a chemical that's caused degradation. Typically, those seals will be swollen, will appear sticky and gummy. So for the most part, very different appearance of a seal that's seen chemical degradation versus high temperature. Although I do want to point out that there are some chemicals that will also cause the O-ring to appear hard and brittle. You can also see the effects of thermal expansion or a volume swell and the effect that it causes on a seal material, as well as installation damage, all creating leak paths. We're going to sneak past this break time since we're near the end here. I'll quickly provide some guidelines for rapid gas decompression. If your system is approaching 500 psi, it warrants taking a look to see if you need to consider seals that are better performing at rapid gas decompression. From the references that I've seen and the resources out there, there seems to be more of a range of when it's understood that you need to start considering your seals with those pressures. Typically that range is around 500 to 600 psi. Anything below that typically don't have to worry about rapid gas decompression. But as you're approaching these higher pressures is when you need to consider the effects, the potential effects of rapid gas decompression. Also, I just want to point out that damage caused by this can occur from one cycle or over many cycles. Over many cycles, it usually is a matter of fatigue that's created inside the elastomer material as those bonds, as those connections that we saw between the polymer chains are stressed over and over again, can create a fatigue type situation, which can also lead to O-ring failure. So ways to manage rapid gas decompression would be understanding what your system pressure is, keeping your pressures low, below 500 to 600 psi. You also have to be aware of the concentration of the gas that's in your system and its ability to penetrate the seal. So you need to understand how that gas material, at what rate that it's able to penetrate into the elastomer or diffuse into that material. That also has a big effect on whether rapid gas decompression is something that you need to take a look at in your system. There are some guidelines on acceptable decompression rates. The thing that I want to point out is that it's not the initial part of decompression that usually causes the issue. It's from the final portion of depressurization that will usually cause your seals to fail. So just providing there a rule of thumb that I located in the reference that I provided there. I'm going to forward past this slide since we're starting to run late. But if you have any additional questions on rapid gas decompression, feel free to contact me so we can discuss potentials in your system and what you might be able to do to make sure that you have that situation under control. There are some international standards for testing which can provide you some solutions as well in selecting your seal materials. I had already mentioned this, excuse me, earlier in the presentation. But just as a general rule of thumb, understand at low temperature, the performance of your seal is going to be affected by pressure. And the general equation is provided there for determining how pressure is going to affect your low temperature seal performance. Our last topic that we're going to discuss here is on shelf life. I want to try to squeak it in quickly here. There seems to be a very big misunderstanding on shelf life. Shelf life only applies to seals in their uninstalled condition. And if you look at the standards for shelf life, what they do is provide a definition of the conditions by which your seal materials can be stored. But once the seal material is installed in your application, in a valve, or in any other equipment, the shelf life standard no longer applies to those seal materials. And then finally, I'm showing you the special alloy materials for NACE acceptability. We don't, unfortunately, have enough time to go through this today, but if you have specific questions regarding NACE and materials which are suitable for your systems, please let me know. Okay, so real quickly, let's test ourselves to see if the hour and a half that we've spent together this morning has been fruitful. And let's see what we learned. So I have some simple questions, and let's see how well we can do with them. So raw gum rubber manufacturers assign a unique compound number for each material recipe. Based on what we learned this morning, would you think that that would be true or false? The answer, of course, is false. We've learned that the raw gum manufacturer is not the manufacturer that's making the rubber compound. So it's actually the rubber compounder that is assigning the unique compound recipe, which gives us the information that we need to know about performance of that material. The second question is, all polymers are plastic or elastic material? And of course, we all know now that this is false. So all polymers and plastics, all plastic and elastomer materials, are polymers, but not all polymers are plastic and elastic materials. Which gives you an easy answer to the next question, which is all plastic and elastomer materials are polymers. We know now to be true. Aaron, I can see that we have a question, but due to our time constraint on here, is it okay if I take that question after? Okay, Buna-N is compatible with methanol. It is true. And of course, you can think back now to what I said is think of that EPRs and Hnbr materials as sort of opposing each other. Petroleum-based lubes are best lubes for EPR seals. And I'm sure everyone knows that the answer to that is indeed false. All FKM seals have the same chemical compatibility. Now that you realize there are many different types, there's type 1, type 2, or type 3 FKM materials, and they all vary in chemical resistance and temperature resistance, we can easily answer this question as to be false. FFKM seals have 2 times the thermal expansion as other seal materials. And we know this to be false as well, and that the thermal expansion can be as much as 3 times the thermal expansion of other seal materials. Number 8, FFKM seals are the best choice for saturated steam at 200 degrees C. And if you remember, I had mentioned that above 300F, pretty much the only choice that you have there in that application is FFKM seals. Question 9. While the low temperature performance of nitrile seals varies, they all have the same chemical resistance. And I'm sure you can all see this question as pretty ridiculous, knowing that as the acrylonitrile and butadiene ratios fluctuate, not only does low temperature performance, but so does chemical resistance. And then finally, explosive decompression is only a concern if my system media is liquid. Hopefully you would recognize that that is also false, as these are concerns in systems containing dry gas. That pretty much concludes what I had available to discuss with you, just to get sort of the basics of seal materials. My current areas of research have been on selecting hard coatings and soft lubricants to prevent metal-to-metal diffusion bonding. Some of the research that I'm currently working on, and the intention there is to find a better barrier than some common barriers such as silver plating, which tend to break down at higher temperatures. So I'm hoping that the time that we spent together was fruitful. At least I hope it was eye-opening, and that we were able to gain a better understanding of what you need to know when you're working with seal materials, and how to ask better questions. So Debbie, I'll turn it back over to you, and we can address any questions that there may be.
Absolutely. Marcy, thank you so much for your informative presentation. I also want to thank our audience for being with us today. There's an awful lot to consider when choosing the right elastomer. If you have additional questions, feel free to contact us using the Contact Us widget at the bottom of the screen. All Engineered to Perform webinars are available on the Swagelok website at michigan.swagelok.com under the Training tab. In addition, this entire presentation will be available on demand later today, and you'll be able to be emailed a link to save or share with your team. For anyone that has an interest on on-site training, we do have a tube fitting and bending class here at our Farmington Hills facility on September 20th. That is an all-day training. Just send us a message in the chat function if you have an interest. So thank you all very much for your participation, and have a great rest of the day.